In the real world, the information within a signal is almost certainly accompanied by a garbage, the noise. We do not need the noise, so we need to eliminate it or at least attenuate it. This is where a frequency filter enters the game, and the most common type is the Butterworth filter. It finds its application in many areas, such as audio processing, instrumentation, communication systems, and control loops. This video will discuss its frequency response, pole locations, its transfer function, and how the transfer function affects the shape of the frequency response. The defining characteristic of a Butterworth filter is that its passband is designed to be as flat as possible, or in other words, maximally flat. In contrast, other filter types, such as Chebyshev filter, exhibit obvious ringing characteristics. It comes with a cost though, as the maximally flat filter means that the transition from passband to stopband is wide compared to filter type that has ringing characteristics. As frequency moves to the cutoff and beyond, the magnitude decreases smoothly and monotonically, unlike its Chebyshev counterpart that has some ripples. For an analog low-pass Butterworth prototype, this is the square of its frequency response magnitude. Here, n is the order of the filter, and omega c is the cutoff frequency. Given this function, how do we determine the system transfer function? At this point, we only know the frequency response of the filter, but we don't know the transfer function. We start from the square of the frequency response, then we rewrite this as a multiplication of h and h conjugate. If we restrict the impulse response of the filter to be real, then from the conjugate symmetry of the Fourier transform, the conjugate of h is equal to the frequency response evaluated at negative omega. Therefore, the previous equation becomes a multiplication of h at positive omega with h at negative omega. To switch to Laplace transform, we change j omega to s. To find its roots, we should set the denominator into 0 as our first step. Next, we move the number 1 to the right side of the equation. Then, we move the denominator from the lower side of the fraction to the right side of the equation. Minus 1 is equal to a complex number where the phase is equal to pi, added by integer multiples of 2pi. We have now reached the final expression for the magnitude and phase angle of S. Let's take n equals 2 for moderate complexity and better clarity. The poles are located on the unit circle with angular interval of 90 degrees, or a quarter of 360 degrees. At first glance, we thought we might be looking at an unstable system, but that's not true. The poles on the left side of the imaginary axis belong to h of s, while the poles on the right side to the h of minus s. To construct the transfer function, take the poles from the left side of the imaginary plane, then assign each of them to the denominator of the transfer function. Does the order of the Butterworth filter have anything to do with the shape of frequency response? Let's draw a bird plot of the frequency response for n greater than 2. In the passband region, the response is pretty flat. At high frequencies, though, the response declines quickly. For the Butterworth filter, the cutoff frequency is defined as the frequency when the magnitude has declined by 3 decibels. The number of poles controls how sharp the stopband slope is. Each pole contributes 20 decibels per decade of attenuation beyond the cutoff, so the second-order filter has a Rolloff rate at 40 decibels per decade. This is the conclusion of today's lesson on Butterworth filter. If you want more content like this, click the subscribe button so you won't miss our next content. Don't forget to leave your thoughts in the comment section. Thank you, and see you next time.